All right. Well, I hope you enjoyed lunch. Now I get to keep you awake and excited throughout the wonderful world of moving data from place to place. I'm going to talk a little bit about Marmaray, our Spark ingestion and dispersal platform. First, a little about me. My name's Eric Sayle. I've been at Uber for about 4.5 years. I've been working on the Hadoop data platform team for about 2 years now. So we're going to talk a little bit about the mission of our team, sort of an overview of what we're doing at Uber with data, why we need an ingestion and dispersal framework in the first place, a bit of a dive into Marmaray and how it works, talk a bit about how we're dealing with some problems like completeness and deletion, talk a little bit about how we're configuring and monitoring the jobs, and then some learnings that we've had. So the Uber Apache Hadoop platform team mission is to build products to support reliable, scalable, easy-to-use, compliant, and efficient data transfer, ingestion and dispersal, as well as data storage using the Apache Hadoop ecosystem. In addition to Marmaray, we also we have members on our team who are responsible for the Apache Hudi project that we actually leverage with Marmaray. So, what are we talking about when we want to do data transfer? We're looking for something that can go from any source to any sink. It can be very expensive to write a bunch of custom pipelines to, say, ingest data from MySQL, and then a completely separate pipeline can ingest data from Kafka, and then a completely separate pipeline can take data from Hive and then put it into Cassandra. We want there to be ease of onboarding so that you can fairly easily add new sinks, new sources. There's business impact, and it really can be important where the data lives and the data store location is. Data in Hive can be very slow to query. Data in Cassandra is very fast to query, but a little more expensive to maintain. And we wanted something built on top of Hadoop ecosystem. So we built Marmaray, any source, any sink. Open sourced in September, link to our blog post. So why do we need this in the first place? At Uber, we've got business events coming in from all over, and really, in order for us to get meaningful insights, we need all of our raw data to be stored in one location, our Hadoop data lake, so that our data analysts can go and look at it and determine how we're doing, where we can improve, deal with experimentation, that sort of thing. So we will go ahead and ingest all of the data into the data lake, and then we'll build derived data sets off of that. We want to make sure that the data is reliable and correct, and so we base everything that we're doing off of strictly schematized data. Everything that's being produced has a schema that it's associated with, and we do not handle any sort of schema inference. Everything is explicit, and then we can maintain multiple different data pipelines. All right, so once we have everything in Hive, why disperse it? Well, we need now to get those derived data sets into other locations that can actually serve live traffic. Hive and even Presto isn't quite fast enough to serve all of the many queries they need to answer in order to serve our apps. So we have to go ahead and push that out. Before we had Marmaray, we had very many duplicate and ad hoc dispersal pipelines. Something specific for MySQL, something specific for Cassandra. And so we want one single platform that can be extended for our future dispersal needs. So we have automated schema management in Marmaray, integration with our monitoring and alerting systems. We're tied with our workflow orchestration tool called Piper, and it's open sourced and should be extensible. So right now, one of our major stories is our Uber Eats recommendations. So all of the data about everything that anyone orders is loaded into our Hadoop data lake. A machine learning model is run against that to produce recommendations that is then dispersed using Marmaray out into a Cassandra instance, which is actually what is serving live on the app the data that comes back to say that you should also be ordering other Japanese restaurants. So let's talk a little bit about the Hadoop data system at Uber. So we have various data producers that will produce their data over here on the left. We use an Avro-based library for emitting to Kafka to maintain schematized data. Marmaray will go ahead and ingest that data into Hadoop, stored in the Hudi file format. And then Marmaray can then also disperse that data out to online data stores. Analytical users can directly access the data in Hadoop, build their derived data sets. And then we have a schema service sort of underlying all of that to make sure that the schemas are consistent and maintained throughout. Come on. And so we are actually ingesting from MySQL and Kafka, as well as internal store called schemaless. And then we're working on Cassandra ingestion as well. They go in through Marmaray, and then we actively have support for Cassandra and S3 dispersal, as well as the data we load onto HDFS. So let's talk a little bit about the components. This is basically what Marmaray consists of. You have some input storage system, and you're going to go ahead and convert through a source connector the data into our intermediate format. We use a generic record Avro-based format for all of the data that we process. It'll run through some number of converters to get into that format. It will run into some more converters that will convert it from the intermediate Avro format into what you need for your sync. And then it will run from the sync connector into the output storage system. At the same time, we have a work unit calculator that's responsible for determining how much each batch will process, and a metadata manager that stores the checkpoints so that we know how to continue. We have the schema service, as mentioned before. We have error tables for error data. There is a config store we have internally for storing all of the configuration for all of this. And we're also producing out to M3 and other monitoring systems the metadata about our processing. So let's drill a little bit into why do we have this schema service and what does it do. So we have the schema service so that we can pull a schema by name and by version of a particular data feed. Usually this is tied for us, for an external process, this is really tied to the Kafka data feeds because there's no standard inherent schema behind any of the Kafka data. For something like Hive, the schema service that you'd be talking to would be the Hive metastore itself, similar for Cassandra. And so then from the schema service, you get a reader that knows how to take the binary data of whatever the raw format is, convert it into your schematized generic record with all of the typing information correct. Similar, we have a writer for taking that intermediate data and turning it back into the binary formats required for the sync. All right, so let's talk a little bit about the Metadata Manager. Metadata Manager is here to store the checkpoints so that we know where to continue from on any given job. So we'll take some persistent storage. You can store it in HDFS or Cassandra right now. At the beginning of the Spark job, we're going to load in from the persistent store the existing checkpoints. Throughout the job, we'll have different components that are trying to read, okay, what is the existing checkpoint? How do I find the next batch of data? And then write back, okay, I now have read up until this point, so get ready to store. And then once the job has completed successfully, we'll write that back to the persistent store. Any failures that happen partway through, we won't write back to the store, and so you'll automatically retry the existing from the existing checkpoints. We also have a fork operator. This is to help us to not completely fail if there are error records. So if I run through a bunch of data on Kafka, we have a specific schema given for that data, and some of the records simply aren't able to be processed. I don't want to fail the entire job because there are 3 or 4 records and I have successfully processed 95%. So what we can do is we can split this into 2 RDDs. One is the schema conforming records. Those will continue on throughout the pipeline to actually be written out to the final data store. The other are error records. We can track those error records, stick them in an error table, and look at them later. We can reprocess them if there was some anomaly and it wasn't really an error. We can communicate with the upstream to figure out what the data should have looked like and be able to fix it and replay it. and just be able to track, how bad is it? Is it 100% of the messages failing? Is it 2 messages? What is the issue? So the way this executes is we'll run through a fork function. The function basically takes every record and tags it with a value. In the success error case, it's going to be a 1 or a 0, depending on whether it was a success or not. It will then produce 2 RDDs out that you can look through and then filter by the ones who have succeeded and the ones who have failed. The error records, as I mentioned, will continue onto the error table. The success can go on. And then we persist the tagged records on disk so we can very quickly retrieve both sets without having to recompute the entire DAG. So it's designed to be easy to add a new source and sync. Basically, all you have to do for a new source is implement 2 interfaces. There's a source interface that says how you read the data from the source, and then there's the converter that takes the data that you've read from the source in whatever automatic format it has and convert into the generic record intermediate form. We also support writing into multiple systems, so I can take a single Kafka feed, process it through into the generic record, and then I can have multiple different output systems off of that same feed. So in this case, I can write to 2 completely separate Hive tables. You could write to a Hive table and a Cassandra table at the same time. And it would continue to process. The way our DAG is set up, we have support for multiple syncs. So our jobs have 2 main components. The first is JobDags, and the second is JobDagActions. So JobDag is sort of our main unit of work. It's going to be everything from the source to the sync, all the conversions required, everything that executes. JobDagActions are going to be additional actions that are taken after the JobDag has completed that aren't as important to cause a failure. So, for example, after we're done completing, we will report all our metrics out for monitoring. If reporting of metrics fails, that's not really that important. We should continue to persist a successful state. We should continue to, the next run should go ahead and pick up everything from as it was. But we should, so that's why it's separate as an action. A JobDag, on the other hand, if anything in the JobDag fails, the whole thing fails, we have to restart and recompute. When we were building this, we ran into the need for running multiple JobDags at the same time. Just due to the frequency of data arrival, the number of messages in our Kafka topics, and the average record size and complexity of the schema, it was too expensive to run a single JobDag, a single topic in one Spark JobDag. So there has to be one driver for every single Spark job that we execute. And we have 2,000 plus Kafka topics that we're processing. We're trying to load most of them at 30-minute intervals. Just the overhead of the extra drivers is too high. So we needed to build a new system so we can run multiple in a single JobDag. And for this, we built the JobManager. So now we can take a single Spark job and we can ingest. We have, I think, 500 topics in some of our larger ones. It'll execute multiple JobDags. It'll manage the ordering so that the ones that take longer actually end up starting first, so you have fewer executors waiting at the end. It will manage this shared Spark context that they'll all be using. It's designed so that any single one of them can fail, any of the Kafka topics can fail, and not affect any of the others. They'll continue on to finish as normal. And we've also built into it locking so that we can't accidentally run 2 Spark jobs that are ingesting the same Kafka topic, writing to the same HDFS path, overwriting and corrupting the data that we have there. All right, let's talk about completeness and deletion use cases. So what is data completeness? So particularly when talking about Kafka topics, we're going to be producing messages pretty frequently. We want to make sure that we have ingested into Hive all of the messages, or the analysis isn't going to be quite correct. So what we've decided to do is to bucket everything into 10-minute buckets. So we will get a count from the upstream Kafka system. There's actually a special tool that's monitoring this. So for this particular 10-minute window, we have produced this many messages. Each message is tagged with the timestamp of production so that we can tie it back to the same 10-minute bucket. And then we will process it in the sink. And so what we can do is we can track, okay, I have gotten all of the messages up until this point. As you can see sort of on the right here, the oldest 2 buckets that you can see are completely full. We've missed some portion of messages in that 3rd bucket. We have the next bucket is completely full, and then the rest are sort of catching up as we read from the various partitions, trying to get to the most recent time. So why bucketize? Why can't I just run queries on the source and sinks directly? It can work if you have a small data set. But for billions of records, it's really expensive to just be running a count constantly, saying, oh, yeah, for this partition, yesterday I have 10 billion records produced upstream. Do I have 10 billion downstream? No, not yet. OK, run it again in an hour and see. That gets very costly. So if we get our 10-minute buckets, we can sort of count as we process and save a lot of time. It's not quite 100% guaranteed. Duplication can counter data loss. So if I look at my records, and I say, yes, in this 10 minutes I've produced 500 records, there could have been a loss and a duplication happening at the same time and counting it out. But with high probability, we're very close to getting actually all of the messages through. So in order to monitor completeness, we just have to track the records at every section through the pipeline. So in this example, reading from Kafka again, we will track all of the records coming in from Kafka, and we'll have some count. Then we will produce, from the source converter, we'll produce success records and failure records, as we talked about earlier. And then the success records will continue onto the sync converter. The failed records go out to the error table. We'll track the counts of both of those. And then from the sync converter, we have the same success or failure. The success records will go ahead and continue on to the output, in this case, Hudi ingestion. The failed records go back out to the error table. And again, we're tracking all of the counts. So internally, for Marmaray to be internally complete, the input count should be the same as the input error records plus the output error records plus the actual successful output records. If this isn't true, we can track that we have an internal consistency problem, fail the job, recompute. All right, so let's talk a little bit about deletion now. So this is sort of our old way of storing Kafka data in Hadoop. As the Kafka messages come in, as I mentioned before, they are timestamped individually. We go ahead and partition them into day buckets. And so we have data up, in this case, up until 2018. This is clearly an old slide. And so as we're writing into sort of our older files, we're writing, if we're running every 30 minutes, we're making a lot of small Parquet files, about 40 megabytes. It's a lot of data. Hadoop is unhappy with that. So we have an external stitcher job that's going to come through, take all of the small files that are more than usually about 2 days old to make sure that we don't have more coming in later, and then write them into fewer larger files that Hadoop handles much better, which is fine. But now I want to delete. The old architecture that we have really only lets you append. You can't really come in, update a record, and remove it. You'd have to go in, find your 4 megabyte file, edit it by hand, and then rewrite it. To find out if a record's there, you have to scan the entire partition, opening every single file, reading through it, looking for the keys. Is it there? And with the GDPR requirements, one of the requirements being data deletion, we have to be able to come in through and very quickly remove data if user requests for it. So our answer to that was actually the Hudi project, which we've integrated with for all of our Kafka ingestion. And so what Hudi will do is it maintains metadata about the table for a series of commits. So as your data comes in and you execute a batch, you will produce, in this case, it seems 4 files for this first batch. We'll go ahead and write all 4 files out. And Hudi will log a commit in its metadata. We'll go ahead and run another batch. OK, we've got 3 more files worth of data. We'll go ahead and write those out. All right, then in my third batch, we come in and we actually have some updates to the data, and maybe deletions of all the fields, masking of PII, something like that. So what Hudi will do is it will come in and it will write another file with the same file ID. So the F1 at the beginning of the file is this ID of the file, with the TS3, the new timestamp in the file. So as you query the data set, Hudi knows how to read this metadata, find out what the most recent commit is, the most recent timestamp is for each file, and only be reading that file. And then after some time goes by, it will go ahead and clean up the old TS1 version of that file, and the data is safely removed. All right, let's talk about configuration. So the configuration that we have right now is pretty much YAML-based. You can't really read this. It's not terribly important. But basically, we have a bunch of parameters for the sources and sinks that you can configure. So I can tell you what Kafka topic I'm reading, where are the Kafka brokers to read from, how many bytes am I reading, how many messages am I reading, and then as you write, what parallelism do I want to use, where are the metrics coming from. All of that is stored in the YAML format. We support currently, most of our jobs are running through an internal manager, and it calls out to that. That's all internal, though. For the open source, mostly what we do is you can write the files out to HDFS. We'll go ahead and read the configuration files off of HDFS as you run the job. For monitoring and alerting, we have a pluggable framework. You can implement a reporters class that goes and can report to whatever metrics. Internally, we're using M3. We also log to the console log, so you can see it in the Spark console. This is sort of some examples of metrics that we have. Again, maybe a little hard to read here. We have rows processed per execution, how far behind we are from current. The middle is the output row count, which ideally matches the rows processed, or we have errors. And then the bottom is just sort of an idea of runtime. So learnings. So from Spark, we ran into a lot of issues with off-heap memory usage of Spark, causing yarn containers to be killed. So we had to be very careful with Spark tuning and how we were tuning memory and how we were storing everything in the persist layers to make sure that we're not creating too many file maps that then go into off-heap memory. We had a lot of issues for a while with overloading of the external shuffle server, so we had to be very careful about how we were processing the data, how we were repartitioning the data as causing a shuffle, and being able to persist the data back in memory so that it could retry easily if we had a failure. We basically did all of our data processing on Parquet. Parquet comes with a very good compression rate for columnar data, as well as having the inherent schema built in that we were able to use to read and write. And yeah, we get better record compression in Parquet with column alignment. So if you can sort the data by a particular field, it can use a good delta compression in order to reduce the data on disk. We also had a couple of issues when tuning where we would just scan the entire data set to find the correct partition, correct offset to start with. That caused the Kafka SRE team a few headaches. So we had to negotiate with them for a tool that they gave to us that allowed us to find the right offsets to start from. And then on Cassandra, so our default Cassandra distribution is SS table streaming. So it bypasses the front end, writes SS tables directly into all of the Cassandra servers. It sort of bypasses all of the throttling and monitoring mechanisms that Cassandra has. The plus side is you get very fast writes. The downside is you can actually cause issues with the Cassandra cluster. So we had to go ahead and re-implement a CLI-based, CQL-based insert interface as well for Cassandra for the larger data sets. All right, so if you're familiar with sort of this landscape, a lot of these concepts sound pretty familiar. We talked with the Goblin team a lot about how to implement this. And so a lot of the concepts are copied directly. As far as why we didn't actually just use Goblin, Goblin was really designed to be an ingestion-only framework, and we did want an ingestion and dispersal, any source, any sink. Also, Goblin is built based on the MapReduce framework, and so the issue is that MapReduce simply isn't quite as fast as Spark is. Spark does a lot more in-memory computation, and so you can get 10x or so performance off of re-implementing it in Spark. But here is the link to Goblin. Here I have a bunch of useful links for Marmaray, for Hudi, Michelangelo is the machine learning team. M3 we've actually already talked about. And now I'll jump into a demo. Okay, so I have here a pre-prepared setup on my laptop. I have Hadoop installed. I have Cassandra installed, and I'm going to go ahead and produce some records in Parquet format into my Hadoop cluster and disperse them into my Cassandra instance. These are all single node instances, but it gives you kind of an idea of how this would work. So currently I have my configuration test.yaml and this test Parquet directory, which is currently empty. Yes, it's currently empty, which is where I'm going to go ahead and write the datasets. So if we look at this test.yaml, you can see kind of what would go into a particular configuration. So for Cassandra, we need to know what is the name of the cluster, what is the key space we're going to be writing into, what's the table we're going to be writing into, what key is going to be the partition key for the table. I don't currently have error table enabled at all. Cassandra thrift address. And then for Hive, where am I loading from? We require a job name to store in the Metadata Manager. Okay. So if I run Spark shell, I'm just going to go ahead and produce a test data set that I can write out in Parquet. So I'm making a very simple data set here. I've got an ID and a name. ID is an integer, name is a string, and I just have 3 records that I've produced in this data set. And then I can go ahead, forgot to export my configuration so that it can actually read correctly. Okay. So now if we look at the test Parquet directory, I have a subdirectory in here called 1. And it has one Parquet file and the success file written when I wrote out the Parquet data. So what I can do now is connect to the Cassandra cluster, use my Marmaray key space. Oops, left over from last time. All right, I have nothing. So I'm going to go ahead and run my Spark submit with my Parquet to Cassandra job that is written, available on the open source repo. Pass in my jar and the path to my configuration file. We'll run for about a minute or so. So what we're running now is we're connecting to the Cassandra instance. We're validating that the table exists, or in this case that it doesn't. It will go ahead and create the underlying Cassandra table for me, load all of the data from that Parquet file into it, and then report that it has succeeded. So now I can describe the tables, and those should both come back. So I have the metadata that's going to tell me what I've dispersed, and then I have the table that I've created that has all the data. Oh, that's a terrible color combination. There we go. So you can see from the metadata, I have my job, my test Parquet Cassandra. It's got the timestamp that I loaded it, which is just now, and it's loaded the 01 directory. It's just going to do a lexicographical run every time to see if there's anything newer than the last thing that it's run. And so now that I've done that, I can also, whoops, not what I wanted to do. Marmaray. Once again, terrible color combination. So now I've loaded my 3 records with their IDs into Cassandra. Okay, that's great. Now what? Well, that's very useful, but it'd be great if we could actually update, add new records, see what happens if I run it again. So I'm going to go ahead and run the Spark shell again. So I have now taken 19, which we already have here, and I've updated its name, as well as adding number 17 with a new string. Then I'll run the job again. Same exact arguments. All of the metadata is managed by the Metadata Manager. I don't have to do anything. I just keep running this. And now I have updated the name for number 19 and added the ID number 17. And so basically, this is what we're running when we're running Cassandra dispersal. We also support features like TTL, so we can actually delete the data after some time, as well as you can specify particularly what the input time is if you want to do something like a backfill with older data that you may not want to have overwrite newer Cassandra data. Yeah, so that's the data that we have in Hive and then in Cassandra. And then we want to look at the metadata table. And so now, by default, we store 5 entries in the metadata, so you can see what has happened recently. I have a new update with a new checkpoint. I can run this one more time. I have not added any new data. And we'll see that it makes another checkpoint entry with the same values because there was nothing to process. Cool. All right, that's everything I have.